So in this video we are going to discuss third chapter matrices Vsaqs. First question, if matrix x minus 1, 2, y minus 5, z 0, 2, 1 minus 1, 1 plus a, which is equal to 1 minus x, so 2 minus y, 2, 0, 2, 1 minus 1, 1. Then find the values of x, y, z and a. Here given two matrices, given that the matrices are x minus 1, 2, y minus 5, and here z 0, 2 and 1 minus 1, 1 plus a, so which is equal to here 1 minus x, 2 minus y, and here this is z, so 0, 2 and here 1 minus 1, so 1 only. See, observe here, so in place of here we have to find the x, y, z and a values we have to find here. So here this is 1 minus x, this is 2 only, this is 2 and here also 2 here. See, observe that, so here both are 3 by 3 matrices only, both are 3 by 3 matrices, so that's why here corresponding elements are equal. So here x minus 1, which is equal to corresponding element is 1 minus x. So from this we can find the value of x. So x plus x is equal to here 1 plus 1, so 2x is equal to 2. So from this we get x is equal to 1. So again here, so corresponding element y minus 5 is equal to minus y. So from this here this corresponding element. So here y plus y is equal to 5. So from this 2y is equal to 5. So y is equal to 5 by 2. So here clearly the corresponding element z. So z is equal to 2 only. So that's why here z is equal to 2. And here to find the value of a, so a here, this corresponding element is, so 1 plus a is equal to 1. So here a is equal to 1 minus 1, which is equal to 0. So therefore here x is equal to 1, y is equal to 5 by 2. So z is equal to 2 and a is equal to here and a is equal to 0. See, like this we can find the x, y, z values. The next question is, define the trace of a matrix and find the trace of a is equal to 1, 2, minus 1 by 2, 0, minus 1, 2, minus 1 by 2, 2, 1. So here, what is the trace of a matrix? So definition of trace of a matrix. So the trace of a matrix is defined as the sum of the principal diagonal elements, the sum of the principal diagonal elements in a square matrix is called trace of a matrix. The sum of the principal diagonal elements in a square matrix is called trace of a matrix. Here, given that, so to find the trace of this matrix, given that capital A is equal to here, so 1, 2, minus 1 by 2, and here 0, minus 1, 2, and here minus 1 by 2, 2, 1. See, what are the principal diagonal elements? These are principal diagonal elements. So now therefore, so trace of A is denoted by TR of A is equal to sum of the principal diagonal elements. So 1 plus minus 1 plus 1, so which is equal to 1 minus 1 plus 1. So plus 1 minus 1 gets cancelled 1. So therefore clearly we can say that, so trace of A is equal to 1. Trace of A is equal to 1. The third question is, if A is equal to 1, 2, 3, 4, B is equal to 3, 8, 7, 2, and condition is given 2x plus a is equal to b, then find x. So here given that the matrix A is equal to 1 2 3 4 and the matrix B is equal to here, so 3872. Now condition is given here 2x. Since the condition is 2x plus a is equal to b, so from this you have to find the x matrix. That means so 2 into x is equal to, we can write b minus a. So now from this, so 2 into x is equal to matrix B is, we have 3 8 7 2 and minus matrix A is 1 2 3 4. Now corresponding elements, so subtracting here 3 minus 1 and 8 minus 2 and here 7 minus 3, so and 2 minus 4 we get here, so 3 minus 1 is 2 and 8 minus 2 is 6, 7 minus 3 is 4 and 2 minus 4 is minus 2. So now here, so 2x is equal to, we have 2 6, so 4 minus 2, and from this to get the value of matrix x is equal to, so here, so divide every element by 2, that is 2 by 2 and 6 by 2, so 4 by 2 and minus 2 by 2, so finally we get 2 by 2 is 1, so this is 3 and 2 minus 1, so which is the matrix X. The fourth question is, construct a 3 by 2 matrix whose elements are given by, so Aij is equal to 1 by 2 into modulus of I minus 3j. So here, so you take that, let a 3 by 2 matrix, let a 3 by 2 matrix capital A is equal to, so considering that 3 by 2 means 3 rows and 2 columns, so this is A11, so here A12, A21, A22, A31, A32, like this. If you consider here 3 rows are there and 2 columns are there, this is a 3 by 2 matrix. Now here, so one represents the rows and second one represents the columns. So here we have given, we have Aij is equal to here, so 1 by 2 into modulus of I minus 3j. So I minus 3j this is. So from this we have to find the elements now. So first element to finding A11 is equal to, so here I is 1, j is also 1. So 1 by 2 into modulus of, this is I is 1 minus 3 into 1, so which is equal to 1 by 2 into here 1 minus 3, so which is equal to minus 2. So modulus of minus 2 is always plus 2. So that's why 1 by 2 into 2, so which is equal to 1. So A11 is equal to 1. Similarly, here you have to find the A12. A12 is equal to, so 1 by 2 into, here I is 1, so j is 2, so that's why 3 into 2, so which is equal to 1 by 2 into, here 1 minus 6, so which is equal to 1 by 2 into 1 minus 6 is, which is 5, minus 5 this is, so here modulus of minus 5 is always plus 5, so that's why A12 is equal to 5 by 2. A12 is equal to 5 by 2. So similarly here we have to find that, so A21 is equal to, so here 1 by 2 into, in the same condition, I is 2 minus j is 1, so that's why 3 into 1, so which is equal to, we get, so 1 by 2 into, so this is 2 minus 3, 2 minus 3 is minus 1, so 1 by 2 into modulus of minus 1, that is plus 1 only, which is equal to 1 by 2. And similarly A22 is equal to, so 1 by 2 into, here I and j both are 2 only, so that's why in the same condition I is replaced by 2 and j is replaced by 2, so we get here 1 by 2 into, so this is 2 minus 6, and here minus 4. So 1 by 2 into this is minus 4. So which is equal to 4 by 2. So 4 by 2 is 2. And similarly here A31. So A31 is equal to here. So I is 3 here, J is 1. So A31 is equal to 1 by 2 into modulus of I is 3 and J is 1. So that's why here 1 by 2 into, so this is 3 minus 3, which is equal to 3 minus 3 is 0. So that's why 1 by 2 into 0, so which is equal to 0, 1. Next A32. A32 is equal to 1 by 2 into modulus of I is 3 minus J is also 2 here. So 3 into 2 here, which is equal to 1 by 2 into 3 minus 6. So which is 1 by 2 into this is minus 3. Modulus of minus 3 is plus 3 only. So that's why 3 by 2. See, we get like this. So therefore capital A is equal to, we have so A11, A12, A21, A22, A31 and A32. So in this corresponding elements, if you replace A11 is equal to 1 and A12 is equal to 5 by 2, A12 is equal to 5 by 2 and A21 is equal to 1 by 2. So and A22 is equal to 2, A31 is equal to 0 and A32 is equal to 3 by 2. So which is the required 3 by 2 matrix. The next question is, if A is equal to minus 1, 3, 4, 2, B is equal to 2, 1, 3, minus 5 and X is equal to X1, X2, X3, X4, then A plus B is equal to X given condition. Find the values of X1, X2, X3 and X4. So here given that the matrices are capital A is equal to here, so minus 1, 3, 4, 2 and B is equal to here, so 2, minus 2, 1, 3, minus 5. So X is equal to, we have here, so X1, X2, X3, X4, so the matrix X. But what is given here, A plus B is equal to X. So this is given condition. So what is A plus B? So the sum of the two matrices. That means here matrix A is minus 1, 3, minus 1, 3, 4, 2 and plus matrix B is here 2, 1, 3, minus 5. So which is equal to the X matrix, that is X1, X2, X3, X4. So now adding the corresponding elements here. So this is minus 1 plus 2 and here 3 plus 1 and here 4 plus 3, 4 plus 3, 2 plus minus 5. So adding the corresponding elements here. So which is equal to here X1, X2, X3, X4, the matrix. See, observe here we get minus 1 plus 2. So which implies 1 and 3 plus 1, 4, 4 plus 3 is 7 and 2 minus 5 here, that is minus 3. So which is equal to X1, X2, X3, X4. See here both are 2 by 2 matrices only. So that's why, so if both the orders is same, the matrix order of both is same. So that's why the corresponding elements are equal. So therefore we can say that, so X1 is equal to 1, X2 is equal to 4, X2 is equal to 4. Corresponding elements are same if order of the matrices is same. X3 is equal to 7 and X4 is equal to, so minus 3. See, like this we can find the X4 is equal to minus 3. So like this we can find the X1, X2, X3 and X4. Next question is, if X minus 3, 2y minus 8, Z plus 2, 6, this matrix is equal to matrix 5, 2, minus 2, A minus 4. Then find the values of X, Y, Z and A. See here, if you take the given matrices, so X minus 3, 2y minus 8, Z plus 2, so 6. So this is a 2 by 2 matrix which is also is equal to 5, 2, minus 2, so A minus 4. So this is also 2 by 2 matrix. So both matrices order is same. So that's why corresponding elements are equal. Here corresponding element is now x minus 3 is equal to 5. So from this we get x is equal to, this is 5 plus 3. So from this x is equal to 8 we get. And similarly here, so 2y minus 8, this corresponding element is equal to 2. So from this 2y is equal to 2 plus 8 and 2y is equal to 10. So y is equal to 10 by 2 which is equal to 5. So therefore y is equal to 5 we get. And similarly here the corresponding element is z plus 2 is equal to, here corresponding element is minus 2. So now z is equal to here minus 2 and this also minus 2. So now z is equal to minus 4. This is the corresponding elements. Then so now next corresponding element is 6 is equal to a minus 4. So from this 6 plus 4 is equal to a. So 10 is equal to a. So therefore a is equal to 10. So like this we can find the x, y, z and a values. Seventh question is, if a is equal to matrix 1 2 3 3 2 1 and b is equal to 3 2 1 1 2 3, find 3b minus 2a. So here given that matrix A is equal to 1 2 3, so 3 2 1. So and b is equal to, so given 3 2 1 3 2 1 1 2 3, so 1 2 3. So now 3b minus 2a, 3b minus 2a which is equal to 3 into matrix B. Matrix B is we have, so 3 2 1 and 1 2 3 here minus. So 2 into matrix A is, we have 1 2 3 1 2 3 and 3 2 1 1 2 3 and 3 2 1. So which is equal to, this is multiplying every element by 3. This is 9, 3 into 2 is 6, 3 into 1 is 3 and here 3 into 1 is 3, 3 into 2 is 6 and 3 into 3 is 9 and minus here. So multiplying every element with 2. So this is 2 and 2 into 2 is 4 and this is 2 into 3 6, 2 into 3 is 6, 2 into 2 is 4 and 2 into 1 is 2. So now, so subtracting the corresponding elements, here 9 minus 2 and 6 minus 4 and 3 minus 6. So here 3 minus 6, so 6 minus 4 and 9 minus 2. So what happens here, which is equal to, we get, so 9 minus 2 is 7, so 2 and minus 3 here. So this is minus 3, 3 minus 6, 6 minus 4 is 2, 9 minus 2 is 7. So like this we get, therefore, so 3b minus 2a which is equal to, we get 7 2 minus 3 2 7. So like this we can find. So next eighth one is, the question is, if a is equal to I 0 0 minus I, then show that a square is equal to minus I. So here given that matrix A is equal to, so I 0 0 minus I, so A is equal to I 0 0 minus I. So now A square is equal to, we have to multiply the matrix A 2 times, which is equal to I 0 0 minus I. So into again I 0, so 0 minus I. So then if you multiply, this is first row, first column, suppose if you multiply, so this is I into I and plus 0 into 0. Again first row, second column multiplying here, I into 0 and plus 0 into minus I, plus 0 into minus I. So second row, first column multiplying, so that is 0 into I plus here minus I into 0, and second row, second column multiplying, that is 0 into 0 plus minus I into I, minus I into minus I, so which is equal to, so we get A square is equal to, so here I into I square and plus 0, and here 0 minus 0, so then here 0 minus 0, Again here 0 minus into minus is plus, I into I is I square. So here we get clearly a square is I square 0 0 I square. So we know that I square value is equal to minus 1. So that's why I square is replaced by minus 1, 0 0 minus 1. So here the value of I square is equal to minus 1. So that's why here a square is equal to we have so minus 1 0 0 minus 1. So which is equal to, if you take minus common, it can be written as 1 0 0 1. We know that 1 0 0 1 is the unit matrix, it is denoted by I only. So that's why, so clearly we can show that a square is equal to minus I. So next question, if a is equal to 2 4 minus 1 k and a square is equal to O, that is null matrix, then find the value of k. See here, given that matrix A is equal to 2 4 minus 1 k. So now here a square, first I am finding a square. A square is equal to a into a, which is equal to 2 4 minus 1 k into again 2 4 minus 1 k. Both are 2 by 2 matrices. Matrix multiplication is possible. So which is equal to first row, first column, if you multiply 2 into 2 plus 4 into minus 1. Again first row, second column, 2 into 4 plus 4 into k here. So now second row, first column, that is minus 1 into 2 plus minus 1 into 2 plus k into minus 1 plus k into minus 1 here. And second row, second column, so minus 1 into 4 and plus here k into k here, k into k we get. So which is equal to, clearly we get, so here 4 minus 4 and here 2 into 4 is 8 plus 4k and here minus 2 minus k and here minus 4 plus k square plus k square. So this is a square is equal to, we have here, so 0 and this is 8 plus 4k and here minus 2 minus k and here minus 4 plus k square. See what is given here, a square is equal to O. So therefore, so given here the condition, since a square is equal to O, so from this what is we get a square, here we have a 0, so 8 plus 4k and minus 2 minus k and minus 4 plus k square which is equal to, so the null matrix is here 0 0 0 0. So that's why here corresponding elements are, if we equate, so 8 plus 4k is equal to 0. From this 4k is equal to minus 8. So from this we get k is equal to minus 2. Again corresponding element is here minus 2 minus k is equal to 0. From this minus 2 is equal to k. So that implies k is equal to minus 2 we get. And here minus 4 plus k square is equal to 0. From this k square is equal to 4. But here k is equal to, we can take plus or minus 2. So that means finally what we have to take here. So if k is equal to 2, so that implies a square is not is equal to null matrix. See here. So if k is equal to 2, here 8 plus 4 into 2, that is 8. So here minus 2 that is minus 4 and here 0. So that's why when k is equal to 2, a square is not is equal to O. So if k is equal to minus 2, so then that implies a square is equal to null matrix. See here, k is minus 2, 8 minus 8, 0. And k is minus 2 plus 2, that is 0. And k is minus 2 here, minus 4 plus 4, that is 0. So therefore, if k is equal to minus 2 only, a square is equal to O, null matrix. So therefore, k is equal to minus 2 only we have to consider. K is not is equal to plus 2. In this video, we are going to discuss matrices, Vsaqs continuation. 11th question, define symmetric matrix and give an example. Solution, definition of symmetric matrix. Definition of symmetric matrix. A square matrix capital A is said to be symmetric matrix. A square matrix capital A is said to be symmetric matrix if A transpose is equal to A. See, this is the definition of the symmetric matrix. A square matrix capital A is said to be symmetric matrix if A transpose is equal to A. For example, here, suppose the matrix A is equal to, so general matrix of 3 by 3, suppose A11, A12, A13 and A21, A22, A23, A31, A32, A33. So this is the square matrix of order 3 by 3, general square matrix of order 3 by 3. Suppose A is a square matrix, A is a symmetric matrix. Suppose this is a square matrix already. Suppose A is a symmetric matrix. So here, so A12 is equal to A21 and also A13 is equal to A31. So A32 or A23 is equal to A32. See, this is the condition. Suppose if A is a symmetric matrix, so that's why we can give the example here. So the example of symmetric matrix is capital A is equal to, as per this, so A12 is equal to, that means A12 means here the element, suppose here if I take 1, A11, here if I take 2, so A12 is equal to A21, both are the second row first element, A13, that means suppose if I take here 4, A13 is equal to A31, both the elements are same, and A23, that means second row third column element, that means if I take here 5 and A32, that means third row second element, that is here 5, rest of the elements you can take anything, suppose see here. So A12 is equal to A21, so A13 is equal to A31 and A23 is equal to A32. So like this, any example you can give for symmetric matrix. For symmetric matrix you can give like that any example by taking the elements. A12 is equal to A2, that means A12 means first row second column element is equal to second row first column element, and A13 means first row third column element is equal to A31, that is third row first column element, and A23 is equal to, that means second row third column element is equal to third row second column. Like that, if you take any elements, the rest of the elements you can take other elements, like that you can give the example. Here A12 is equal to A21 is equal to here, so 2, A13 is equal to A31 is equal to, so here 4, so A23 is equal to A32 is equal to here 5. See, like that you can give. This is not compulsory. You can take any elements are equal like this. The rest of the elements here you can take any other element. That means you can observe that clearly principal diagonal elements you take any other elements, and these elements you can take the equal as you wish. And also we can say the examples. This is suppose example 1. See here, zero matrix identity matrix, that means unit matrix. So unit matrix, zero matrix or unit matrix. So diagonal matrix, see here, diagonal matrix. So matrix are always symmetric matrices. are always or symmetric matrices. Or symmetric matrix. So that's why you can give the example here. Any zero matrix is also a symmetric matrix. You can give the example. So unit matrix of order 2 or order 3, you can give the example for symmetric matrix. And diagonal matrix, any diagonal matrix except the diagonal elements, remaining all elements are equal to 0. That like that also you can take the example for symmetric matrix. Like this we can say the definition of the symmetric matrix is a square matrix capital A is said to be symmetric matrix if A transpose is equal to A. That means transpose of matrix A is always is equal to the same matrix. So that's why we can say that we can define the symmetric matrix is A transpose is equal to A. The next question is 13th one. If A is equal to 2 minus 4 minus 5 3, then find A plus A transpose and A into A transpose. It is also very important. So in the given problem, so given that capital A is equal to matrix A is equal to, so 2 minus 4 minus 5 3. See what we have to find here, A plus A transpose. So now I am finding A transpose. A transpose is equal to, see first row writing into the column 2 minus 4 and second row writing into the column. Transpose means the rows interchanging into the columns. So we get A transpose. Then what we have to do? A plus A transpose. So therefore A plus A transpose is equal to, so matrix A is 2 minus 4 minus 5 3 and plus A transpose, that is 2 minus 5. So minus 4 3 here, so which is equal to the corresponding elements are adding here. So 2 plus 2, the corresponding elements, and minus 4 and plus minus 5. So and here corresponding elements are minus 5 plus minus 4 and here corresponding elements are, so 3 plus 3. So we get here which is equal to 2 plus 2 is 4 and minus 4 plus into minus is minus 5 which is minus 9 and minus 5 and plus into minus is minus 4. So minus 5 minus 4 is minus 9 and 3 plus 3 is 6. So clearly we get A plus A transpose is equal to 4 minus 9 6. Similarly we have to do that. A into A transpose. Now A into A transpose is equal to matrix A is 2 minus 4 and minus 5 3. So which is multiplying with the A transpose, that is 2 minus 5 minus 4 3 here. So which is equal to, we get, so multiplying first row first column, so that is 2 into 2, immediately write plus and minus 4 into minus 4 here, minus 4 into minus 4, first row first column multiplied, first row second column, that is 2 into minus 5 here, 2 into minus 5 plus immediately and minus 4 into 3 here, first row second column multiplying here, minus 4 into 3 here, minus 4 into 3, and similarly here second row first column, writing in the place of second row first column here, minus 5 into 2, minus 5 into 2, immediately plus 3 into minus 4 here, 3 into minus 4, and also here, so second row second column multiplying minus 5 into minus 5, so minus 5 into minus 5, again immediately plus, so 3 into 3 we can write, 3 into 3 like this. So second row second column multiplied, so we get here which is equal to, if you simplify this is 4 and plus here 4 into 4 is 16 and here minus 2 into 5, that is minus 10 and here minus 4 into 3, that is minus 12 and here minus 10, 5 into 2, minus 5 into 2 and here minus 3 into minus 4, that is minus 12 and this is minus into minus is plus 25 and here plus 9. So clearly we get here, if you simplify, so 16 plus 4, that is 20, and here minus 10 minus 12, that is minus 22, and minus 10 minus 12, which is minus 22, and here 25 plus 9, this is 34. So like that we get A into A transpose is equal to 20 minus 22 and minus 22, 34. We get both are 2 by 2 matrices only here. Columns of the first matrix is equal to rows of the second matrix. So that's why multiplication is possible. Resultant matrix order is also 2 rows and 2 columns here. So that's why resultant matrix order is also we get 2 by 2, like this we can do. So the next question is, if A is equal to minus 1, 2, 3, 2, 5, 6, 3, x 7 is a symmetric matrix, then find x. See what is given here. Given that the matrix A is equal to minus 1, 2, 3, 2, 5, 6, 3, x 7. See, and also what is given here, since capital A is a symmetric matrix, is a symmetric matrix. See, we know that as per the definition of the symmetric matrix here, so A12 is equal, that means first row second column element, A12 is equal to A21, we know that. And also, so first row third column element, that is A13 is equal to, so third row first column element, see here, third row first column element, first row second column element is equal to second row first column element. So A13 is equal to, so here A31. And also similarly here, so we know that A23, that means what, second row last column element, so is equal to, so third row second column element, that means what, A32. See here clearly, if you observe in the matrix, A12 is equal to A21 is equal to 2 only, both are. So A13 is equal to A31 is equal to, both are 3 only here. So as per that here, so A23 is equal to A32 only. So that's why therefore here we can take that to find the value of x. So A23 is equal to A32 you can take. So that means what, which is implies A23 is equal to what here, 6, which is equal to A32 is what here, x. So therefore clearly we can write, so the value of x is equal to 6, like this you can find simply if the given matrix is a symmetric, the value of x. The next question is, if A is equal to 0, 2, 1, minus 2, 0, minus 2, minus 1, x 0 is a skew symmetric matrix, then find x. See here, given that matrix A is equal to 0 to minus 1, 0 to 1 here, and minus 2 minus 2 0, minus 2 and minus 1 x 0 here. See, and also what is given, so capital, since capital A, matrix A is a skew symmetric, so is a skew symmetric matrix. See, clearly we know that when it is a skew symmetric matrix, we have the condition. What is that? So A12, that means first row second column element is equal to minus A21. See here, both are 2 only here. A12 is equal to, A12 is 2, A21 is minus 2. So that's why both are same only. And also here, that means with opposite sign. And again here A13, that means first row third column element is also is equal to minus A31. So A13 is equal to minus A31. So you can observe here clearly. And also here A23 A23 is equal to minus A32 here. A23 is equal to minus A32. We have these conditions actually. But here, which condition is applicable to find the value of x? A23, that is minus 2, which is equal to, so minus A32. That means what here? Minus A32 is x. So both sides minus gets cancelled. So simply you can write x is equal to 2. So like this we can find if given matrix is a skew symmetric. And also you can observe that in the skew symmetric matrix the principal diagonal elements are all equal to 0. So like this you can find the value of x. Next 10th question is if a is equal to 3, 0, 0, 0, 3, 0, 0, 0, 3. So then find so a to the power of 4. So here given that a is equal to 3, 0, 0, 0, 3, 0, 0, 0, 3 and we have to find the a power 4. So now a is equal to, if you take 3 common from this, we can write 1, 0, 0, 0, 1, 0. So 0, 0, 1. So this can be written as a is equal to 3 into, we know this 1, 0, 0, 0, 1, 0, 0, 0, 1 is unit matrix I. To find the a power 4, so operating whole power 4 on both sides, whole power 4 on both sides. So then we get here, so a to the power of 4 is equal to, a to the power of 4 is equal to, this is like ab whole to the power of m. So that is 3 power 4 into I power 4. We can write here, suppose ab whole to the power of m is equal to a to the power of m into b to the power of m. Same like that 3i whole to the power of 4 is equal to, so 3 to the power of 4 into I to the power of 4 and a power 4 is equal to here 3 power 4 is 81, 3 into 3 into 3 like that 4 times. So into I power n is equal to I only. I power n is equal to, always we get I. So that's why here this is also I power 4 is also is equal to I only. So that's why 81 into I. So finally if you write, so 81 into, again unit matrix 1, 0, 0, 0, 1, 0. So 0, 0, 1 if you write, then finally we can write a power 4 matrix is equal to 81, 0, 0 and 0, 81, 0 and 0, 0, 81. So like this we can find the, so matrix a to the power of 4. The next question is 11th question, define skew symmetric matrix and give an example. Skew symmetric matrix definition. A square matrix capital A is said to be skew symmetric matrix if transpose of A is equal to negative, that means additive inverse of A. Additive inverse of A means minus A. So A transpose is equal to minus A. Suppose for example here, so we have the general matrix, suppose we have capital A is equal to the general square matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So here to give the example of this is here clearly to say that, so if A is a skew symmetric matrix, so then A12 is equal to minus A21. A13 is equal to minus A31. And also A23 is equal to minus A32 in any square matrix, then we can say that capital A is a skew symmetric matrix. If this is a capital A is a skew symmetric matrix, so then we can say that, so here A12 element is equal to minus A21, A13 element is equal to minus A31, A23 is equal to minus A32. So that means to write the example of this is, so example we can take that, see suppose let A is equal to what I told you here, A11, you write any element. That means you have to observe that in the skew symmetric matrix, the principal diagonal elements are always equal to 0 only. Here 0 and A12 is equal to minus A21. A12 if you take 1 minus A21 you take minus 1. And A13 is equal to if you take 2 and here you take a minus A31 here. So that's why minus 2. So and again here A23 suppose if you take a 3 and here A minus A32. So that means minus 3 and rest of that means particularly in the skew symmetric matrix the principal diagonal elements are always equal to 0 equal to 0. So that's why like this we can say that here A12 is equal to minus A21, A13 is equal to minus A31, A23 is equal to minus A32. Like that you can give number of examples. So here which is a skew symmetric matrix, and also clearly here you can write that here. So here A12 is equal to minus A21 is equal to here 1 and A13 is equal to minus A31 is also is equal to here. So this is 2 and you can observe that A23 is equal to minus A32 is equal to here. So 3. So like that we can A23 is equal to minus A32. So that's why like that you can observe that here. So A12 is equal to minus A21, A13 is equal to minus A31, A23 is equal to minus A32. You can observe in the matrix A also. Clearly you can write the example like this. The next question is if A is equal to cos alpha, sin alpha and minus sin alpha, cos alpha, then show that A into A transpose is equal to A transpose into A is equal to I. So given that matrix A is equal to here cos alpha, sin alpha and minus sin alpha in the second row and cos alpha. See, we know that transpose of A. What is transpose of A? A transpose is equal to. So just writing first row into the first column, that is interchanging the column into or row into column. Right? Cos alpha, so sin alpha, row writing as a column. And second row writing as column, that is minus sin alpha, cos alpha. So we get the A transpose, see here. So interchanging the rows into columns, we get A transpose. Now multiplying A into A transpose is equal to. So both the matrices multiplying here. So this is cos alpha, sin alpha and minus sin alpha, cos alpha in the second row. So and multiplying this is with so cos alpha minus sin alpha and here sin alpha, cos alpha. See, when you multiply here, see first row, first column you have to multiply. That means cos alpha into cos alpha into cos alpha, that is cos square alpha, immediately plus and sin alpha into this sin alpha, that is sin square alpha. See, first row, first column multiplied. First row, second column elements you have to multiply. Cos alpha into minus sin alpha, that is minus cos alpha, sin alpha. So again immediately plus. So sin alpha into second element, sin alpha into cos alpha, that is sin alpha, cos alpha. Similarly, second row, first column. So minus sin alpha into cos alpha, that is minus sin alpha into cos alpha. Plus, here this is minus sin alpha into cos alpha. Immediately plus cos alpha into sin alpha. That is it. So cos alpha into sin alpha. Again, second row multiplying with the second column. See, minus sin alpha into minus sin alpha. minus sin alpha into minus sin alpha. Minus into minus becomes plus. Sin alpha into sin alpha, that is sin square alpha. Again you have to put the plus immediately. So cos alpha into cos alpha, that is cos alpha. So cos square alpha, that is cos square alpha. Cos alpha into cos alpha, cos square. See, observe here, so these two terms are same only, but opposite in sign. Sin alpha cos alpha plus and minus sin alpha cos alpha with minus gets cancelled. And also here, so plus cos alpha sin alpha minus sin alpha cos alpha gets cancelled. We know that cos square theta plus sin square theta is equal to 1. So cos square theta plus sin square theta is equal to 1 we have. Same like that, cos square alpha plus sin square alpha is also is equal to 1. A into A transpose is equal to, we get here 1, and that second element is both are gets cancelled, 0 here and here 0, and here we get again 1, so which is equal to I. So that's why we get A into A transpose is equal to. So that implies A into A transpose is equal to I. Similarly, suppose if you take A transpose into A, so which is also is equal to, first writing A transpose, that is cos alpha minus sin alpha, and here, so sin alpha, cos alpha, this is A transpose. So A transpose multiplying with matrix A, so that is cos alpha, sin alpha, and here minus sin alpha, cos alpha, multiplying this is A. Then what we get? See again, first row, first column multiplying. Cos alpha into cos alpha, that is cos square alpha, plus immediately. So minus sin alpha into minus sin alpha, that is plus sin square alpha. Minus into minus is plus only here. Again, first row, second column. Cos alpha into sin alpha, that is cos alpha sin alpha. Cos alpha sin alpha, immediately plus, but here minus sin alpha into cos alpha. So that is minus sin alpha cos alpha. Minus sin alpha cos alpha. Again here second row, first column multiplying. Sin alpha into cos alpha, that is sin alpha cos alpha. Sin alpha cos alpha. Again cos alpha into minus sin alpha, that is plus minus sin alpha cos alpha or cos alpha sin alpha. See, observe here. Again second row, second column multiplying. Sin alpha into sin alpha, that is sin square alpha, plus. So here cos alpha into cos alpha, that is cos square alpha. So here if you observe, this is also minus and plus, this is minus plus, gets cancelled. There we get 0 only. Same like this property, cos square theta plus sin square theta is equal to 1. So A transpose into A is also we get. So 1, 0, 0, 1. So which is equal to I only. So therefore here that implies A transpose into A, suppose, which is also we get I only. So therefore finally we can write A into A transpose is equal to A transpose into A is also is equal to I. So like this we can prove. Next question is find the cofactors of the elements 2, minus 5 in the matrix. Minus 1, 0, 5, 1, 2, minus 2, minus 4, minus 5, 3. So given matrix is here, given that the matrix is, suppose, minus 1, 0, 5, 1, 2, minus 2, minus 4, minus 5, 3. See, we have to find the cofactor of the element 2 here. That means 2 presenting in the second row, second column. So cofactor of 2 is equal to, it presents in the second row, that means minus 1 whole to the power of second row, second column, so which is minus 1 whole to the power of 2 plus 2. So 2 represents the rows and these 2 represent the columns, so it presents in the second row, second column, so minus 1 whole to the power of 2 plus 2, and after deleting this second row, second column, we have the matrix minus 1, 5, minus 4, 3. So determinant of into minus 1, 5, so minus 4, 3. So now which is equal to minus 1 whole to the power of 2 plus 2 is, that is plus 1, so which is plus, so into determinant of this is determinant of minus 1 5 minus 4 3, that is minus 3 and minus of minus 20, minus of minus 20, minus 4 into 5 is minus 20, so which is equal to minus 3, however it is plus minus 3 plus 20, which is equal to 20 minus 3 is 17. So cofactor of 2 is equal to 17. Similarly, we have to find the cofactor of so minus 5. So minus 5, if you see that this is which presents in the third row, second column. So that means which is multiplied with minus 1 whole to the power of third row, second column, so minus 1 whole to the power of 3 plus 2 into determinant of so minus 1 presenting row and column, that means third row, second column, deleted we get the matrix minus 1, 5, 1, minus 2, so determinant of minus 1, 5, 1, minus 2, so now which is equal to minus 1 whole to the power of 3 plus 2, that is minus 5, minus 5 means which is minus, so minus 1 whole to the power of 5, that means minus here. So here we get determinant of this is minus 1 into minus 2, that is 2, and immediately minus 1 into 5, that is 5, so which is equal to minus of minus 3, so which is equal to here we get 3, so therefore cofactor of minus 5 is equal to 3 and cofactor of 2 is equal to 17, like this we can prove. The next question is, if omega is the complex cube root of 1, then show that determinant of 1 omega square 1 omega square 1 omega is equal to 0. So here given that omega is the complex cube root of 1. So omega is the complex cube root of 1. So when omega is the complex cube root of 1, we have the two conditions, that implies 1 plus omega square is equal to 0. This is one condition exists. And also the second condition is, so 1 into omega square, that means omega cube is equal to 1. So now here the given determinant, taking now LHS, so that is the determinant of 1 omega square and omega square 1 omega. See here what I am doing is here operating either C1 to C1 plus C2 plus C3. So this is C1, this is C2, this is C3 column. So here applying that C1 to C1 plus C2 plus C3. Adding C1, C2, C3 and writing in the place of C1. So now which implies determinant of this is, so C1 is 1 omega square. Adding that 1 plus omega square. Again omega plus omega square plus 1 omega plus omega square plus 1. And again omega square plus 1 plus omega. So now here second column and third column is as it is. Second column and third column is as it is. See, if you observe here 1 plus omega square or omega plus omega square plus 1 or omega square plus 1 plus omega, both all are same one. So we know that sum of the roots of the cube root of unity is here 1 plus omega square. Sum of the roots is equal to 0. So that's why, so which can be written as here. So 0 here. First column is 0. So omega square 1 omega. So here we know that since 1 plus omega square is equal to 0. So that's why in a square matrix all the elements of a row or column is equal to 0. Then the determinant of this matrix is 0. Any row or column in a square matrix, all the elements are equal to 0. Then the determinant of that matrix is 0. The next question is, if Matrix A is equal to 1, 0, 0, 2, 3, 4, 5 minus 6x and that A is equal to 45. Then find x. So now here, given that matrix A is equal to 1, 0, 0, so 2, 3, 4, 5 minus 6x. Now and also given that A is equal to here, determinant of A is equal to 45. So now what I am doing is finding determinant of A. Determinant of A is equal to, so 1, 0, 0 and 2, 3, 4, 5 minus 6x. So which is equal to, see here 1 into 1 present in row and column deleted. We get determinant of 3, 4 minus 6x. And next second element you have to take here plus, minus, plus. So that's why here minus 0 into here 0 presenting row, that is first row, second column deleted, we get determinant of 2, 4, 5x. So 2, 4, 5x. And next here plus 0, last element is considered as a with plus, so plus 0 into 0 presenting column, that is third column, and first row deleted, we get determinant of 2, 3, 5 minus 6. Like this we can find the determinant. So now however which is equal to here, we get 1 into, so this is 3 into x, that is 3x, and minus here minus 6 into 4, that is minus 24. So however these two elements we get 0 only. So but here given that A is equal to 45, so therefore 45 is equal to, so 1 into 3x plus 24, 1 into 3x plus 24. From this we get 45 minus 24, which is equal to 3x. So from this 21 is equal to 3x. So from this, so x is equal to 21 by 3, so which is equal to 7. So like this we can find the value of x. So after finding the determinant, so therefore x is equal to 7. Next question is find the determinant of the matrix 1 square, 2 square, 3 square, 2 square, 3 square, 4 square, 3 square, 4 square, 5 square. So that A is equal to, consider that 1 square, 2 square, 3 square, so 2 square, 3 square, 4 square, and 3 square, 4 square, 5 square. So now here expand it, then we get 1. So 2 square is 4, 3 square is 9, 2 square is 4, 3 square is 9, and 4 square is 16, 3 square is 9, and 4 square is 16, and 5 square is 25. So now determinant of A is equal to, that A is equal to, so determinant of 1, 4, 9, 4, 9, 16, and 9, 16, 25. So now here which is equal to, so 1 into, so 1 into 1 presenting column, row deleted, first column, first row, then we get determinant of 9, 16, 16, 25. And again second element you have to take with minus 4 into determinant of, so 4 presenting row, that is first row, 4 presenting column, second row deleted, we get 4, 16, and 9, 25 here. And next last element we have to take with plus 9 into determinant of first row and last column, if we delete we get 4, 9, so 9, 16, so which is equal to, we get 1 into, this is 9 into 25, 9 into 25 is 225, minus 16 into 16, that is 256, and minus 4 into here, so this is 4 into 25, this is 100, so minus 9 into 16, that is 144, and plus 9 into this is 64, and minus 81. So what we get here, which is equal to 1 into, so this is 256 and 225 minus 256, that is minus 31, we get, so and minus 4 into this is 100 minus 44, that is minus 44, and here plus 9 into this is 64 minus 81, minus 17. So we get here which is equal to minus 31 and here plus, so this is 176 and here minus 153. So now what we get here, which is equal to minus 31 and minus 153, we get minus 184 and plus 176, which is equal to minus 8. So clearly, therefore, determinant of A is equal to minus 8. So like this we can find. Next question is find the rank of the following matrices. See, given first one is let A is equal to 1 1 1 0. Find the determinant of A. Determinant of A is equal to, so determinant of 1 1 1 0. So now which is a 2 by 2 matrix. Determinant of this is what? 1 minus. So this is the determinant of this is 1 into 0 minus 1 into 1. So which is equal to 0 minus 1. So which is equal to minus 1. So determinant of A is not is equal to 0. So therefore capital A is a non-singular. Capital A is a non-singular matrix. So that's why here, so rank of A is equal to, so order of this matrix is what? 2 by 2. So that's why rank of A is equal to 2. So like this we can find. So similarly here, the second one is given here. So matrix is in 1 0, that A is equal to here also. So 1 0 minus 4, 1 0 minus 4 and 2 minus 1 3. Actually this is a 2 by 3 matrix, but you consider any 2 by 2, this is 2 by 3 matrix. Consider let a 2 by 2 submatrix, a 2 by 2 submatrix of A is B is equal to any 2 by 2 you can take. So now I am taking here 1 0 2 minus 1. So now determinant of B is equal to, we get this is minus 1. So minus 1 minus 0 which is equal to minus 1, which is not is equal to 0. So therefore B is a singular, B is a non-singular. So that's why, so rank of A is equal to, when it is a non-singular and the matrix B is 2 by 2, even though the matrix, given matrix is 2 by 3, so rank of A is equal to 2 only. So next, the third one, suppose if you take here, let A is equal to 1 0 0 0 0 1 and 0 1 0. If you find the determinant of A is equal to here, so determinant of A is equal to, we get 1 into, so 0 1 1 0 and here minus 0 into, this is 0 present in column, plus minus plus, you have to take like that. So 0 1 0 0 we get 0 1 0 0 and here plus 0 into, so this is 0 0 0 1. However, here we get these two elements are 0 only and here 1 into 0 minus 1, we get this is minus 1, which is not is equal to 0. So therefore capital A is a singular. Capital A, therefore capital A is a singular. So when capital A is a singular, so non-singular here, the determinant of it, which is not is equal to 0. So it is not a singular, it is a non-singular matrix. Capital A is a non-singular matrix. So when capital A is a non-singular matrix and it is a 3 by 3 matrix, it is also clearly given 3 by 3 matrix. So that's why rank of A is equal to 3. So whereas if you come to the fourth one, so let A is equal to, if you take, so 1 1 1 1 1 1 and 1 1 1. So if you find the determinant of A, so compulsory we get 1 into 1 1 1 1 and minus 1 into plus minus plus, if you consider minus 1 into here again 1 1 1 1. So here plus 1 into again here, So we get 1, 1, 1, 1, determinant of a. See, any 2 by 2, we get 0 only here. So 1 into this is 0, and minus 1 into this is 0, and plus 1 into 0. So which is equal to 0. Therefore, capital A is a singular. Capital A is a singular. So, and also let a 2 by 2, let a 2 by 2 submatrix, let a 2 by 2 submatrix, so of A. So every 2 by 2 submatrix of A, suppose every 2 by 2 submatrix of A, let every 2 by 2 submatrix of A, if you take, see here, if you consider any 2 by 2 submatrix of A, so which is a singular matrix only, which is a singular, every 2 by 2, let every 2 by 2 submatrix of A is singular matrix only. So singular matrix only. So that's why. So even though the given matrix A is 3 by 3, so here every 2 by 2 submatrix of A is singular. So therefore we can write that rank of A is equal to 1. So like this we can prove that. The next question is solve the following equations. So 2x plus 3y minus z is equal to 0, x minus y minus 2z is equal to 0, 3x plus y plus 3z is equal to 0. So here the matrix form of the given equations, the matrix form of the equations, So capital A is equal to coefficient matrix 2, 3, minus 1, 1, minus 1, minus 2. So 3, 1, 3. And x is equal to here, x, y, z. And here O is equal to origin, that is 0, 0, 0. See, you have to find the determinant of coefficient matrix here. So 2, 3, minus 1, and 1, minus 1, minus 2. So 3, 1, 3. If you find the determinant, this is 2 into here. So this is minus 1, minus 2, 1, 3. And here second element is we have to take with minus. So minus 3 into determinant of minus 3 present in column, row deleted. So 1, minus 2, and 3, 3 we get. So here plus minus 1 into we get. Here minus 1 present in row and column deleted. 1, minus 1. So 3, 1. So which is equal to. So 2 into this is minus 3 and plus 2 here. This is minus 3 into. So if you multiply 3 and plus 6 here. So here plus into minus is minus 1 into here. 1 plus 3. So which is equal to 2 into minus 1. And minus 3 into this is 9. So which is equal to minus 1 into this is 4. So we get which is equal to minus 2. And here this is minus 27. And here minus 4. So which is equal to we get minus 29 and minus 33. So which is not is equal to 0. So when that A is not is equal to 0 here. So determinant of A which is equal to minus 33 which is not is equal to 0. So therefore capital A is a non-singular matrix which is a non-singular. So that's why. So here rank of A is equal to order of the matrix. Order is 3 by 3 only, so that's why rank of A is equal to 3. Therefore it has a trivial solution. So the solution is here. So therefore the solution is x is equal to y is equal to z is equal to 0. Like this we can prove.